Yeah, good evening. One and all, we'll be back to the error detection method. This is a topic in second unit and also few topics in third unit. We'll be covering all the problems. In this error detection method, we have longitudinal redundancy check and also we have vertical redundancy check. Now, longitudinal redundancy check theory part was already done in the class. So we are just doing the problems, and this is also called as LRC, and it is also 2D parity check. It is used to detect the burst errors, and the data which the user wants to send is in the form of the tables of rows and columns, wherein it will be arranged in the form of matrix. In order to detect an error, redundancy bit is added to the whole block and this particular block is transmitted to the receiver. With the help of the redundancy check which has been sent to the receiver, you see that the error will be identified by the receiver side. Now assume that we have the frames, 4 different frames which are of 8 bits each, and then the total is equal to 32 bits which is being transmitted. It is divided into the matrix of 4 rows and 8 columns. So we have the original data, and then this data has been transmitted, is being arranged in the fashion of matrix. Now this, what we do is, we are trying to find the exclusive OR of this particular column. So in exclusive, while we are finding the exclusive OR of this particular column, we see that the data, whatever is given, will be 1 or 0. So when we have 0 and 1, we have only 1. So when there is single one, you have 1. When there are 3 ones, you have 1. When you have 2 ones, it is a 0. When it is 4 ones, again it is a 0. And zeros you have, it is a 0. Assume that this one, whatever we received, is what is called as an LRC. Okay, the result is whatever you obtain from exclusive OR of the 4 frames is what is called as LRC. So now the data, original data, along with the LRC is being sent to the receiver side. The receiver, on receiving this, he will try to add up again all the data frames, and once the LRC what you obtain and the sender what the LRC is being sent, if it matches, then it keeps the data. Otherwise, it try to discard the data whatever is being sent by the sender side. Now assume that this particular fourth 0 is being changed to 1. So what happened if this 1 is here? You see that the redundancy LRC what you have to get is 1 here. But when this is 1 and the LRC whatever is being received at the receiver sender side is the same thing, that is, he won't change this. Only the second frame of the fourth bit is being changed 0 to 1, and it just sends the data. That means the transmission of the frame has been having an error. So it been transmitted, or the receiver, when he adds up, you see that there is one particular one here. So the LRC by the sender and the receiver will not match. So the receiver will discard that complete data which is been sent by the sender. Now coming to the vertical redundancy check, it is called as a parity check. And when the number is being sent, you see that the data frame, whatever is sent here, will be adding one more 1 to the right side. So it tries to make the number of ones as an even parity, or it also makes the number of ones as an odd parity. Based on the one, whatever is being added, you see that this is what is called as VRC parity bit, you call it. So now when you have this ones, it is totally 5. So it will add one more 1 to the right side corner, which becomes 6. So this is what is called as VRC. Then immediately what we see is the receiver, when he tries to receive, then looking at this particular one, he will remove this one and then he will just consider the data whatever is being sent by the sender. Now assume that again there is a transmission error. That means the 0, when it is being transmitted, becomes 1. And when it is being sent as is 1101 1111. So what happens is, at the receiver, he will see that the number of ones is not even. So what it does is it will try to discard this particular one based on the number of, based on the bit which is being added as a parity bit on the right side. This is how VRC will work. Now coming to the sliding windows. Here in the small example, we have taken a window size of 3, and then we have an alphabets which are A to H. Now when we are moving the slide, it means that the window size of 3 will only consider 3 bits. Okay, so the window keeps sliding through all the alphabetic. So here what we see is we have ABC, BCD next, then CDE. So this is how it keeps sliding to the end of the frame. This is what is called a sliding window. Now coming to a problematic numerical one, let's assume that the window size is 5, and then we have a frame which is 9 bits. So here what we see is the size is 5, and then we are trying to find which is having the maximum value. So here when we start off the sliding window, we first takes 5, 7, 1, 4, 3. 5 is this window size. So the sum of this is 20. Next it slides to 7, 1, 4, 3, 6. Then we see that the sum is 21. This is greater than the previous one. Then again the slide will move to 1, 4, 3, 2, 6 and 2. So then the sum is 16, which is very lower than the first two. Then it moves to 4, 3, 2, 4, 3, 6, 2, 9. So it is nothing but 24 it is. Then we have 3, 6, 2, 9, 2. So this is nothing but the Windows maximum sum value is 22. So what we see is the maximum size of the window size 5 is the window wherein you have 4, 3, 6, 2, 9. That is nothing but sum is equal to 24. So this particular window is the one which is having the greatest value. This is how the sliding window will work. It keeps moving one bit after the other and selecting the remaining ones till the end of the frame. That is what is called as sliding windows. Now next we'll be doing the shortest path routing, which is in third unit. So as you know, we have different nodes, and then we see that which particular node gives the shortest path. So now here we have this particular problem, which is unweighted graph. Unweighted graph is the one wherein you see that you have all the nodes, but the weight which is being given on the this link which is connecting two nodes is called as weighted. So here we see that this particular node doesn't have any weight. So we are assuming that each one will be 1, 1. So here we wanted to check from 0 to destination 7. So we are moving from 0 to 7. So we can move from 0, 3 and 7, 0, 3, 4, 7, either way. So we can see that 0, 3, 7 is the shortest one because it has only 2, 1, 2. Okay. So then the input next is input is source is 2 and destination is 6. 2 and 6 it is. So 1, 2, 1, 0, 3, 7, 6, or it can go 3, 4, 6. So we have 2, 1, 0, 3, 4, 6 is the one which is shortest. So 2, 1, 0, 3, 4, 6 is the shortest one. Because when it goes here, it is having 2 more bits which are being added. That is what is called a shortest path. Now, this is what is called as a weighted graphs. Because you can see the difference in this particular graph. You don't have the weights on the links, but whereas this is having the weights on the links. So starting node is 0 here again, and the destination is 4. So whichever route you go, you should get the smallest distance. That is what is called as shortest path for the weighted graph. So here we are trying to start at the 0. Okay. When you start at 0, it can either go to 1, it can go to 7. 7, when it is going, it is having the weight of 8. When it's going to 0 to 1, it is only 4. When it is going 0, 1, 2, 4 plus 8 is 12. When it is going 0, 7, 6, it is only 9 it is. Now let's check. So initially you'll start with 0 and all other weights you put it as infinity. And just we see that adjacent values of 0 are 1 and 7. I told you 1 and 7. Okay. And the values on weighted ones are nothing but 4 and 8. So you have 4 and 8. And the update distance values of adjacent vertices of 1 are nothing but, I told you, here if it goes 0, 1 and 2, it is 12, 0, 7 and 6, it is 9 it is. Okay. So now when you are picking the 7, okay, because here the value is 9 totally when you're going like this. But when it is going like this, it is 12. So we are picking the 7, 7 is picked up. So you have 0, 1 and 7 it is. Update the distance of the vertex 7 and then again you're trying to check whether it has to go to 6 or any other way. So 6 has been picked because it is having 9. So then you're trying to calculate the value of it 0, 1, 7, 6 and then again you are trying to check whether 15 is good or 5 is good, 11 is good. Okay. So when you're going 0, 0 to 7, 8 it is, 8 plus 1, 9 it is. Then whether from 6 to 8 or 6 to 5. So here it is becoming 11 it is. But when it is going here, it is becoming as 15 it is. That is what is saying here. Okay. So you are trying to check basically which is the shortest one and then you're choosing that particular vertex and then finally you are trying to reach 4. So fourth one will be going from, so 0, 7, 6, 5 and 4. So the distance is 8 plus 1, 9, 9 plus 2 is 11, 11 plus 10 is 21. So the 21 is the shortest route to reach the 4. This is what all about the shortest path for the weighted graphs and hope you enjoyed the class and then many more problems we can do while you understand this particular lecture. So we'll stop here.